Okay, thanks for coming. We were in the middle with clustering, and this was our main example to study unsupervised learning. And yeah, we've seen a few examples. We haven't seen all the mathematical details of the examples, but we have seen the ones for clustering. And then we mentioned hierarchical clustering. If you have data examples, that there is also a setting where you don't assign just every data point into just one group, but that you have trying to produce an entire hierarchy of groups, right? So this was happening here a little bit, that you see this tree, and this produces at the top level, you only have two main groups, right? But then if you want, or if your user wants, they can go down further in the tree. So if you go down further, then here you're on a level where you have like 10 different groups. So all the individual data points are put into these 10 groups. And you can get much more granular as you go down. At the bottom level, you will have that every point is its own group. So this is a nice way to solve a bit the problem that you don't know how many groups to choose, right? There's not a good answer to that in most of the cases. We discussed a little bit for k-means that, yeah, how to choose the size of the number of the groups. And then we've seen this, different example of not a clustering, but a model which is able to generate data. So it's trained unsupervised on just a collection of images. We don't know what they mean or what label they have, but the model is learning to produce more images. It's done in this a bit strange way, which we unfortunately don't have time to make formal, that there is one network which takes noise, random numbers, so a bunch of random numbers from 0 to 1. From that's a neural network which goes up through all these layers. It produces an image. So here comes the image, and that image is judged by a second neural network which tells if it's real or fake. And that one either gets real or fake images, and that's the job, is to distinguish. That worked pretty nicely for small resolution images, which are just tiny, then life is a bit easier. And just I thought that it's interesting to see what's happening in some real deep learning research. So this was last week. So they did this for much higher resolution images. So these are not real people. These are all fake images. They don't exist in reality. And now in the space of these random numbers, which I mentioned, you can just move from one position to the next. And that's what's doing here. And as you move in the input space, you can observe how is it moving in the output space where it's producing these images. And it looks quite realistic. And again, none of these persons exists in reality, so that's quite strange. Okay, that's a generative model. And yeah, if you see any other funny examples you see in the newspapers or something, then send me an email, then we can maybe briefly show them in the class and discuss. Any comments on this or questions? Okay, let's get back to the more basic but also more formal things. We have seen the k-means algorithm to produce a clustering, right? It was very simple, had these two steps which you need to perform in each round. Yeah, updating the assignments and updating the cluster centers. That's where we stopped last time. We saw that this is actually just the same thing as performing coordinate descent. There is a slight catch here, right? So we talked about this is two coordinates, the blue and the yellow, right? But these are not numbers, right? So, I mean, in reality, the Z is a collection of many numbers, but if you treat them all together, like this entire block of variables, if you treat that as one variable, so to say, then one coordinate, so to say, then this is coordinate descent, right? So fix one of them and completely optimize the other. It doesn't matter if it's one coordinate or a bunch of coordinates, but I'm fixing the yellow ones and I'm completely optimizing all the z variables. So this is the idea. Yeah, what was this L function? So what were we actually optimizing? So it's not so clear when you just look at the algorithm, then you don't know what does it optimize, right? But we did see the objective function. It was right here. So we saw that there is actually an objective function. We kind of convinced ourselves that that's actually the objective function that the algorithm is trying to minimize, right? In each step, either optimizing for these guys or for these guys. And the objective function was, what was it? It was the sum of these within cluster distances, like the points in their group, they should be close to the center of the group. So that's what this is measuring here, right? And we saw that the algorithm is doing that in this way of alternating between the two. I'm mentioning this again because we will need this again, and we are going to slightly modify this objective function. And first, we also trying to interpret this objective function better, like in a probabilistic way. Is there a reason why should you care about? Why should you optimize this one? Why not some other objective function? So, and that's one thing which we're going to do next. But first, I also want to show you a concrete example again. So that's actually where we stopped. In this example, we haven't had time to discuss it last week, but the idea is that on the right, it's not one data point, actually. This is a lot of data points. We are talking about the pixels of this image, right? So there's lots and lots of pixels. Forgot how many. Yeah, I think this is 200 by 300 pixels, so it's 60,000 pixels. Now, what we want to do is we wonder if we can save space, right? The way images are stored on a computer is, right, just all the pixels, we reserve the memory, and every pixel is stored. What's stored there, right? The color of the pixel. So, but there are many colors. There are 16 million colors in some cases. So for every pixel, you need a lot of memory to store which color out of the 16 million, which one is it? So it's, it's yellow, yellow, and then it's blue, blue, and blue, and some other kind of blue. The question is, can we compress this image by using a smaller amount of colors? So what would you say? Could you use clustering to perform such a compression that you don't need 16 million possibilities for each pixel, but that you could deal with less? So what would you suggest to do if you have a clustering algorithm available for you? Then just give you these 60,000 pixels, they are stored. Now, can you compress this data set of 60,000 data points? So, yeah.
You represent each pixel in the RGB space, and then you find n-cut clusters in the RGB space.
So you're saying we should go to the color space and there find a fixed number of clusters, right? And then use just the cluster colors instead of the original colors, right? So, and yeah, that's basically the idea. So you could do this in any space you want. Yeah, you mentioned the RGB space. It could be any space where you can compare two colors. The idea is that every color is a data point, right? But the ones which are close, we just want to replace them, and we've just put one representative for that color group, and that, why not take the mean, the center of this bunch of data points? in the color space. And that's exactly what we are doing here. The only thing you need to decide is how many clusters, right? So, and here is what happens if you just take 10 clusters. So you replace all these, let's say 16 millions. Maybe it was actually only 8-bit, but let's pretend it's 16 million. And we replace them with just 10 colors. So instead of all these shades of blue on the, in this area here, now everything here is assigned the same color, except that bunch here. That's there's 2 variants of blue now, right? But there is not 10,000 variants of blue anymore. No. So that's all that has happened here. It's very easy. For every color, I just replaced it with a centroid, that one of these 10 specific colors, which I defined to be the means of each group. So, and yeah, in which space should you do that? For example, in 3D space corresponding to red, blue, and green, that might be a good choice. There are other color scheme. You can use any you like. As long as you have a distance function, now in 3 space, as long as you have a distance function, you can apply the k-means clustering algorithm. The only thing you need to specify is how many groups do you want. And then, yeah, the result still looks okay. You can still recognize the original image. You can go to more extremes. So here is 3 groups. The interesting case here is when you only get 2 colors. So then you saved an extreme amount of storage, right? Now you just need 1 bit per pixel, which is a huge saving compared to the 16 millions you needed before, but it comes at a price, so now we don't recognize much from the image anymore. But even in this extreme case, it's not completely off. It's not a bad choice, because the centroids of these just 2 groups, they seem to be a good choice to best represent all the colors they are. I mean, half of all the colors they are. Yeah. So that's encouraging. That's also the whole idea of this kind of clustering, right? For the group, you're trying to find a representative, and the mean seems to be a good representative. And yeah, exactly the same thing happening on the second row, original image on the right, and on the left, compression when you reduce the number of groups. So this is also called a vector quantization, and it's a very, very, very simple algorithm. It's of course not the best argument for images, but this idea is very general. You can use this in many, many other places. People even use this idea to compress the weights in a neural network or things like that. So whenever you need to compress something, then that's one easy way to do it. It's not the best for images, but it works. So.
What happens if within a cluster there is a lot of variability, and then the mean is very prone to, like, it's very sensible, not to outliers within a cluster? So can I take the median?
You're asking if you can take the median instead of the mean. That's a very good question. I think people have tried it, but I'm not sure. I've not seen an analogous scheme. Yeah. So you're right. You mentioned you'd be worried if the clusters have very irregular shapes. One is very large, and the other is actually very well centered. And we will discuss a bit in the next lecture that to be a little bit more adaptive, because k-means is quite naive. Every cluster needs to be round, right? It's just a squared Euclidean distance, and they're all treated the same. So there's not much we can do to adapt to such a setting. Yeah. So, but yeah, there is no true clustering anyway. So it's a good question. I don't know about the median instead. So this one you actually implement right in the lab this week. So was the template useful? Does it kind of work? Or so you can try this on any image you like and see what happens when you vary the number of clusters. Also, you can play a bit like how long do you want to run the clustering algorithm, the k-means. We saw that, of course, it's a good way to stop when nothing changes anymore. That's what we did in this example here. Actually, this data you also have in the lab. So when it really stops changing the assignments, then you know you can stop, right? The algorithm is not going to do anything anymore. In a real scenario like here, it might take longer to reach that stage, but it still could. Did anybody run this until the assignments completely stopped changing among these 60,000 pixels? No. Okay. Good. Let's discuss something interesting, which is about this objective function, right? So we found it kind of natural. The k-means algorithm looks natural, and also we saw that it does minimize this function. But it would be nice to understand better, like why this objective function, and is there another motivation for it? Yeah. And there is actually. So we saw this kind of probabilistic interpretations already for ridge regression, and to some extent a bit also for the logistic regression when we were talking about the likelihood of the data, right? So of all these data points, maybe you write them as a matrix again. Given the model, given the parameters of the model. So, and the parameters we have in this clustering model are just the means and the assignments. So. The mu and the z, right? So that's the things. This describe our model, right? Once you have the means and the assignments, then that describes describes the clustering. Now, can we talk about does this actually make sense? Does this have a high probability? And for that, again, we want to use the notion of likelihood. Like, if the parameters were like this, then is the data that we have, is it actually likely that this has produced our data, right? And this is the very important principle of maximum likelihood, which you have already seen from regression and classification, that you ask, so now here's my data, but which were the parameters which are most likely to have produced this data, right? So maybe then I should choose these parameters. So that's a very strong argument why this is a good model, right? So then it makes a lot of sense to do this kind of training, to optimize that function, which is to maximize the likelihood. That's always a good idea, if you know what your likelihood is. So we don't know, but let's actually see. So maybe we can compute it for the case of k-means clustering, and then we will, in the end, we will compare it with our objective function, and turns out they will be the same actually. Let's do this. So the likelihood is the probability of the data, and I will do it for one data point first. So for this data point, how likely is it to happen, to be produced, if my model is given? So if my model is mu and the assignments are this. Okay. What we assume in k-means is actually that we have a very simple model that what does it mean to be in this group, and from that group to produce the data points from the group. So, and what it does, it just uses a normal distribution, the simplest distribution you can imagine. So that's the probabilistic model that we will try now. Once we have such a model, we can look at the likelihood, see if we can compute it, and then we can try to maximize the likelihood. Okay, so I will just use a normal distribution. So now my data is my random variable, and this normal distribution has a mean and a variance, which for the covariance matrix, I will just put the identity. Okay, so which k, which mean? There are many groups, right? We have k groups. And the idea is that each data point is produced from that round normal distribution. Which one? The one from the actual group it belongs to. I mean, we got the group assignment, right? For n, we know which group the point is assigned to. So it's the group k for which we are assigned, right? The set right. So that is the assignment. The nth data point is assigned to the group small k, and that's the one which we use in our normal distribution. And that's the idea, right? That's the most natural idea to use your assignment. Yeah. And that's basically the whole story. So now, this is the only assumption that we make. From now on, it will be easy to actually compute this likelihood, and it turns out we will get an overall likelihood, which is the same thing as we were actually minimizing in the, or which we were optimizing in the k-means algorithm. So now, from now on, it's just a simple computation, and let's do it actually. So I will just do this. It's very nothing happens here. I just do this small trick that. Okay, maybe let's call this k prime. So this is the k prime, which is actually the true one, right? But now I'll just do this naive trick. I'll take a product over all possible groups. So there are k groups, capital K. And now I can this is just to write this in a different way, to use my assignment variables to express what we just said in green, right? The assignment tells you where you assigned. It's 0 or 1. Actually, for all the ones it's 0, there is no contribution here. So all of this stuff is nothing. The product is not there. The only term which is there is the one when the set nk is actually 1, and that's the group you're assigned to. So all that to just say that nothing has happened. This is just a different notation than the first term, right? Do you agree more or less, or unclear? So okay. Yeah, then I will just now plug in the definition of the normal distribution. You have seen this before. 1 to k. Yeah, what was this? It was the e to the Euclidean distance of this thing. So it's minus 1/2 of how far are you away from the center. Yeah, that's it. And then the whole thing is still taken to the power Znk. Again, nothing has happened here. But now we can make our lives a bit easier by talking about the log likelihood, because we don't like products. They are very difficult to optimize. It's very nasty because one term interacts with all the others, and so we want to optimize sums instead. So we look at the log of this whole thing. I'm taking the log on both sides, and actually, so yeah, taking the log of this. Then I'm getting the sum instead of the product, sum over k, of these distances. How far are you away from your actual center? But to make it simpler, we we use all the possible centers, right? And we just write this assignment variable here, right? Because previously this was the exponent, right? And now when I take the log, what happens is that this thing just gets multiplied with the distance, right? So again, nothing has happened. And I just took the minus to the other side as well. So this is the likelihood of one data point. Now we are almost there, but so now what you're actually interested in is not the likelihood of one point, but the likelihood of all the points. But already this almost looks like what we are optimizing at the beginning. So we're almost there. So the only thing is we want the complete likelihood of the whole X matrix, again given these same parameters. These are the parameters of the model. Okay. Yeah, what's this? So now if I have it for 1 point, then yeah, you're saying it's a product, and that's exactly the case. It's a product over all n's. So why is that? Because we assume that each data point is generated independently. That's actually same thing with the faces that we saw being generated before from these strange random numbers. Again, everything is generated independently. We always have this assumption in machine learning that there is one distribution which produces data points, and each data point comes from that distribution, right? But they don't influence each other, right? You can get one data point, you can get the next one, but they all come from the same distribution. What we did before is we said that one data point comes from this distribution. So if you get more than one, if you get n of them, then the probability that you get first data point is this, second data point is that, and you get n different data points happening, then they're random variables, they become n points in space. What's the probability of that constellation, right? That's the likelihood of the whole data set. And that's the product of each data point happening separately. And now we are done. So now we have product over all these guys, 1 to n. And we do get the likelihood, the log likelihood of the whole data set, which now becomes the sum over all data points. So this is the log likelihood of the whole data set, X as a matrix, parameters. And yeah, this happens to be exactly the objective function that we used at the beginning, which we called L of mu and the assignments. Yeah.
So that would mean that the clusters are circular, because we assume that the covariance matrix is I, right?
Yeah, very good point. You're asking why is this now every group is circular, like spherical? And yes, that's the case. So because there is only the identity here, and this is pretty annoying, right? This is groups might not always be circular in real life, right? So what we have here is this is just this circular part, right? It's the distance to the center. It's just measured in a sphere. So you can actually, I mean, the other way to write this is as the inner product, xn minus the center. And that right, that's what it is. So this is circular. So this is annoying. This is not flexible if the shape of a cluster is different, which was your question as well. Okay, how could you fix that? So, and this already suggests it, right? So, because now what we did is we have an identity here in the middle, right? So, but now you could use a general Gaussian distribution, which has a covariance matrix, right? Which means it's an ellipse instead of a circle or instead of a sphere. So then you could use this this more general matrix in the middle, right? So now it was the identity, but now you could use this covariance matrix sigma or whatever it is, and then you would actually get groups which are not spherical but which are an ellipse. And that's what we're going to do later today or then next Thursday when we do so-called Gaussian mixture models. And there it's actually a bit nicer indeed because there's more flexibility to adapt to the groups. But for k-means, this is really spherical, no ability to do that. This has pros and cons, right? On the good side is that life becomes simpler. We don't need to optimize or find any shapes of ellipsoids, right? The only thing we need to find is the mu, the centers. So that's not too bad also, yeah. Okay, other questions, comments? This was a good comment, yeah.
In the PDF of the normal, why don't we add initially the 1 over the root of 2 pi, just because it's a constant and...
Did I forget 1 over root of 2 pi? I probably did, yeah. So I did, yes. That's true. So what I wrote here is all wrong, but what's true is if you add plus some constant in the end, right? So here there is some constant in front, which is what you said, the 2 pi something. And when you take the log, this just becomes a constant which is added to the thing. It's a constant. So I'm going to minimize or maximize this thing, and then it doesn't matter if there is a constant being added to it or not. But yeah, thanks. I forgot the 2 pi.
If you take the identity matrix as a covariance matrix, it's just 1 over the root of 2 pi times the determinant of the identity, which is 1. But if we start thinking about more crazy shapes for the clusters,
yeah.
then
So
constant might become...
yeah, you're right. So you're saying that this is only 1 over square root of 2 pi for the identity. That's true. When we go to more crazy covariance matrices, there might be a different constant, and we will get to that when we do that, which is in the second lesson today. Yeah. But for the identity, it doesn't matter. So, but okay, maybe I should write it. Maybe should I write some c times? So here's a constant.
It's not there yet. It's just at the third line.
And then here there is another constant happening.
There
So
should be a c in the first 2 lines.
yes, there should not be a c here, but something like this, right? Good, thanks. And the c prime here is the log of the c that was there. Yeah. Okay. Yeah, so that's good to know. That's reassuring that it actually does make sense to optimize this objective. It also does make sense from a probabilistic point of view because this is one of the most natural models. You could assume that data is produced in groups, right? That's probably the easiest way you could produce data by groups. And if that's your model, the standard normal distribution, then happens to be this is the k-means objective function to ask which parameters are optimizing the maximum likelihood for this model. Yeah. There was another comment? Sorry. Okay. Yeah. So this is often the case that machine learning models have these two views. One is just the optimization view, which is more close to my background, and also there's the probabilistic view. If you understand really how your data was probabilistically generated, then you can argue about the likelihood and the parameters of such models. Yeah. Okay. So yeah, here is the other view. So that's just purely now that let's say we accept this optimization objective anyway. So we've already seen this now twice on the first slide when we introduced the algorithm, and now when we produce the probabilistic interpretation. So here it is again. This is what we optimize. What we're going to do now is we're going to convince ourselves that what this is doing is actually it's trying to find a matrix factorization, or it's trying to find two matrices such that when you multiply them here, then you get the original data. So you have the data, but you try to approximate it as a product of two matrices. Seems quite simple, but why is it actually the case here? Is that really what we are doing? And yes, it is. And the easiest way to see that is to just, we need to understand how this assignment matrix, right? How is that multiplied with this matrix of means, right? So the M, what's the M matrix is containing all the means as its columns, right? Yes. Sorry, that's the M, capital M matrix. First column is mu1, and so on. There are k columns. Right, this is the M matrix. That's clear. I'm claiming that you can multiply this with the assignment matrix, and the assignment matrix will be containing the assignments as its row. Okay, that's the Z matrix. So both of them have k columns. And so the assignment matrix has one of these assignment vectors for each data point, right? So let's be a bit clear about that. So what I mean by the nth row, like for data point n, I can look at the nth row of it, and what I mean is that this assignment of the nth point, it's 0 everywhere, right? But it's 1 for that k where the point is assigned to. So this is a k vector, and that's one row of my assignment matrix here. So that's, and this dots here, that just means all the columns. So yeah, if I don't want to write Zn because I want to be clear that this is a row of my matrix. So that's where one data point is assigned. And what I'm claiming here is that what we have here what I have in bracket here is actually the data point n, right? This one, how far is it away from its center? And all I'm doing is I'm writing the center of that point by the n matrix times this assignment vector for my point. Yeah, I always mess up the transposes and stuff. So that's what this sum is here. So let's take a moment to see if that's the case. So right, I'm multiplying a matrix with a vector. So this vector here, well, it's a transpose of a row vector, so that's a column vector, which sounds good so far. So that column vector has k entries, they all 0, except the entry where I'm assigned, that's a 1. So what it does is it selects that column of m, which I'm assigned to. So yeah, the ZnK column if you want. So there is one particular column, and that's the column where ZnK is 1. That's where I'm assigned. And if I do this, that's the column I get. So that's my own group representative, that vector. And I can just write it like this, matrix times vector, so it just selects this one column. Nothing has happened. Again, that's just algebra. Now, Do you agree with me so far? No. Yeah.
Do we have objects or types in columns, right? Not in rows?
The data points, are they columns or row? I haven't talked about that yet. Good point, good question. So x here is meant as a column vector. Yeah, that's easier in this case. So, or do you prefer it to be a row vector for the data points? You usually had row vectors, so yes, yeah, you're right. It's maybe more convenient to have them nk, that every data point is a row vector. So let's do that. Yeah. Okay, I still write x. Okay, not yet. So still write xn. So xn is one data point, and anyway, but the xn will maybe be a column of my x. Sorry, a row of my x matrix. That's what you guys are used to. So then that's the next step. So let's see how we get there. But do you agree with me that this thing here, this sum, is actually the sum of can actually be written like this matrix times vector, right? So it only counts the distance to the actual mean where you assigned, and that one I just wrote like this, very very simple. So I get the same term. And now I've done this for one data point. Now let's sum this up over all the data points. And that's what's happening here. That's when we get the next equality here. So why is that? So I'm approximating a bunch of vectors. Let's think of them as column vectors. We did it for one of them, the xn. Now I want to do it for many at the same time, which are just summed up. So the way I do it is I'm going to use this matrix norm here. But it looks strange, but it's nothing than just summing up all the squared entries. So what we have already seen is that if we sum the squared entries of a vector, the x vector, to the mean, then we can write it as this vector 2 norm here. And now if I want to do this for many, many points, then I actually can do this for this X transpose matrix, which has the, okay, you guys asked for it, so now these guys are columns of the X transpose. Right, so that's the X transpose matrix. And that gets compared to M times Z transpose. And yeah, what is that, right? So you can convince yourself that this is just it's just the sum of all these guys. Like for the first, if I do this for the first column here, I get this with n equal 1, right? So for x1, I will get this minus the Z1 transpose, right? I do this for all the columns of this matrix. And what I want is I want the sum of all these vector approximations, a sum over n terms. And that's exactly what this Frobenius norm is, so don't be scared. The Frobenius norm is simply of a matrix. Yeah, let's write this Frobenius norm of a matrix A. It's just the sum of all entries of the matrix. The sum of the squared entries. So sum over I and j of the entries squared. And there is another easy way to write it. I can just say that, yeah, either I sum this first over the columns or first over the rows. It doesn't matter at all. So here we're talking about columns. Actually, that's easier. So I write these two dots to say any row but only column j, right? So that's the j's column. And the sum over the vectors norms of these columns, that's what it is. Or you could also write it as the sum over the rows if you want. You get the same thing. It's just the easiest norm you can define on matrices. It actually happens to be a norm. Yes, so then we are done. After the break, I'm going to go over this again a little bit. And now here, to make this true, just again, now we really made this consistent with the previous lecture. So the data points are rows of the X matrix. You have data point 1, it's here, and you have data point n, which is the last row. And then this equality holds. You can convince yourself now, or let's briefly go over it again after the break in 10 minutes. So. Okay.